Okay, so hi everyone. Welcome to the Bootstrap seminar. We are very happy today to have Karthik Prabhu, who will tell us about the infrared finite scattering and quantum field theory and quantum gravity. Please, Karthik, go ahead.
Great, thank you. So this is recent work done jointly with Gautam Satish Chandran, who's a grad student at University of Chicago, and Bob Wald, who everybody knows is also at University of Chicago. So I'm going to set up this problem just briefly. What we want to look at is scattering when you have massless fields in an asymptotically flat spacetime. And I've this is a cartoon that actually Gautam has drawn and very graciously lent to me. So here I've drawn the conformal picture, the conformally completed picture of some asymptotically flat spacetimes. In most cases, we can think of this as Minkowski, but when I talk about quantum gravity, the inside of the space-time will really not be known, and we'll just work on the conformal boundaries. And so just to orient everyone on what this picture really is doing is you have a point here which is past time like infinity, which is I minus. That's where your massive fields will come in from. And the massive fields will do some funny thing, interact in complicated ways, and they'll emit some radiation. And the massive fields eventually go to future time like infinity, which is I plus. And all the massless radiation they emit goes to null infinity, which is this angle, this slanted line, which is usually called script I plus or scribe plus. And there's also a past boundary from which you can send in massless fields that I haven't done in this diagram. And more importantly, for some aspects of this talk, the null infinities are actually joined at spatial infinity, which you can think of either as a point if you're an exact Minkowski, but for this case, it'll be better to think of it as a very, very large sphere at t equals constant, for example. And I'll introduce the coordinates and all that when we get to it. And the key problem or the key aspect of massless fields that's important in what I'm going to say is the so-called memory effect. And it's the fact that the massless radiation actually has a long time tail, or essentially a zero frequency part on null infinity. So here I'm calling theta as the angular directions. I'm only going to use one theta, but it really is theta and phi coordinates on a sphere. And u is the Bondi retarded time coordinate on future null infinity. And if you look, for example, in electromagnetism, what is the behavior of a radiating electromagnetic vector potential? You start from some value. It doesn't matter exactly what the value is. And then you have these wiggles, which basically tell you radiation and all the scattering happening inside. But as u goes to plus infinity, which is really, really far in the future, the field value doesn't go back to itself. It doesn't go back to the value it started from. And this difference between really, u being really in the past, which is actually near spatial infinity in this case, and u in the plus infinity, which is really in the future, the difference in the values is the memory effect. And this is all classical right now. And generically, the reason we actually do care about this effect is that for some random scattering process, generically, this memory effect will be non-zero. And there's a similar effect in gravity, which, all the formulae I'll explain when I get to it, but it looks exactly the same, but it has two indices instead of one index or something. And in the gravitational case, it's really called the memory effect, because if you look at test masses, which are really far away from where the scattering is happening, so effectively at null infinity, somewhere close to this region here. For example, the LIGO detector will basically function as that when black holes are colliding somewhere really far away. Then these wiggles basically are the oscillations of the different test masses or the LIGO mirrors. And this memory basically tells you that in the end, these test masses are sort of permanently displaced. So your detector will sort of remember that it has not gone back to where it was. And that's the memory effect. And this happens for massless fields in 4 dimensions. So I'm going to stick to 4 dimensions in this case throughout the talk. And classically, this effect has been studied now for a very, very long time. But it plays a very important role when you try to quantize the theory. And in this case, I'll be talking about quantization of the radiation at null infinity. So I'll be agnostic about what the bulk quantization of the theory looks like. So for example, if I'm talking about gravity, it'll really be agnostic about what kind of quantum gravity theory we're looking in the bulk. All I'm asking for is, okay, we'll assume this asymptotic boundary and ask for what the gravitational field or the radiation of the gravitational field or even the electromagnetic field will look like at null infinity. Okay, so I'm going to build up to full quantum gravity or full general relativity, but I think it's instructive to actually start out with the simplest case where a lot of things actually work pretty nicely. And that's the case of massive QED. So what we're going to do is the following. We're going to have some massive charged scalar field, phi, and we're going to couple it to electromagnetism. So this is some complex scalar field which has some charge. So think something like electrons and positrons, even though they're fermions or something, we'll model them by scalar fields in this case. You can also do the fermionic fields directly if you want. The story doesn't really change. But because it's the electromagnetism part that's actually important from what I'm going to say. And you can describe the behavior of the scalar field in the past and future limits as it goes to time like infinity by sort of its Fourier components, which I'm just labeling here. I mean, after this point, I'll never talk about them anyway. But the point is you get some positive, negative frequency parts. And because it's a complex field, you have 4 of them. And you can use this variable P, where P lies on a unit hyperboloid. And this is the usual Fourier description. You can think of P as being the mass hyperboloid, but the mass has been scaled away, so it becomes a unit hyperboloid. And this is completely standard, and we know how to quantize this stuff. So B will be the annihilation, and B dagger will be creation operators in the quantum theory for your particle, and C dagger for the antiparticle, and so on. Okay, but what does the electromagnetic field do? If you go to large distances, so that's large radius r, but at fixed time and angle, then the vector potential behaves roughly as some angular component, which is finite, plus everything decaying. And the radiation is actually captured in the time derivative of this vector potential, which you can, again, think of as a electric field component at null infinity. And as I was mentioning, the memory delta really is the difference of the vector potential in the future and the vector potential in the past. So, or again, you can also think of it as the U integral, where U is the time integral of the electric field. And this description is actually much more useful to see what's going on. Though I might have some sign error or something, but don't worry, that won't play an important role. Okay, so what do we do with this asymptotic radiative field of electromagnetism? We can actually quantize it because you can construct an asymptotic phase space using the electric field as a phase space variable. And this is sort of a nice description that was worked out a long time ago by Abhay Ashtekar. And when you try to quantize it, you basically take your electric field, and instead of just being a classical electric field, it's now an operator value distribution. So I'm going to use boldface for operators instead of hats. And it's, U and theta. I mean, We all know this needs to be a distribution and smeared in with nice test functions and so on, but I'm going to think of it as a U and theta operator, which has some U and theta dependence. And you can write down the canonical commutation relations, which come from the asymptotic Poisson bracket and so on and so forth. And a lot of the standard quantization really goes through. I mean, you have a vacuum state, which is acted on by this operator. You have a whole operator algebra, which is Poincare invariant. And this vacuum state is actually completely determined by its electric field 2-point function, which I've written down here. This I0 plus is the almost standard I epsilon prescription, so that this whole object is a well-defined distribution. This QAB is the metric on the sphere at null infinity. And you can construct sort of one photon Hilbert spaces by just taking test wave functions. So some wave function which now has an index because the electric field has an index. Oh, I should have mentioned this. Capital index is an index purely on the sphere, or you can think of it as polarization indices. So there'll be 2 polarizations and 2 values of this index. And the one particle Hilbert space norm can actually directly be computed from basically the 2-point function. And you get something that looks like this. So in this formula, I've actually used Fourier transforms to go from the time variable u to a frequency variable omega. And this S of omega theta is the positive frequency part of the Fourier transform. That's why the integral is only from 0 to infinity in this case. And once you have the one particle Hilbert space, you can construct an entire Fock space, and that's the standard Fock space that you'll get even from bulk quantization of electromagnetism. But there's a problem in this story, is that if your wave function actually has memory, so if this S had some memory delta, its Fourier transform actually diverges as 1 over omega, 1 over the frequency. And if you put it into this formula, one can easily see that its norm actually diverges logarithmically. So the standard Fock space actually has no states with memory in it. All the states are completely without any memory. And this is the problem when doing scattering theory, because even classically, a generic non-trivial scattering, even if your in state didn't have memory, or if your in state even did not have any electromagnetic radiation or photons coming in, the out state generically will have photons, and those photon things will have memory in them. So the standard Fock space is sort of not enough. It doesn't have enough states to actually describe a generic scattering when you have this memory effect floating around. And this is true even in the classical theory, but it really becomes a problem in the quantum theory because you don't have these states in your Fock space. But we can actually construct Hilbert spaces which do have memory. And it's sort of a method which basically constructs coherent states from a classical solution. So you can start with a classical solution whose electric field I'm denoting by this curly E. And suppose it has some memory delta, which is just its U integral. The way to define this, use this as a coherent state in the quantum theory is to just take your original electric field operator, or we can rewrite this in creation annihilation terms, and map it to a new operator, but shifted by the classical solution times your identity operator. And because we're shifting by some classical object times the identity, all the commutation relations are actually preserved. And this is a automorphism of the original operator algebra. So the abstract operator algebra did not change. All you're doing is adding sort of a classical solution times the identity in the end. And it turns out this automorphism cannot be written as a unitary map on the standard Fock space if this memory is non-zero. But you can find a new Hilbert space of states, which is sort of F with a subscript delta. That's how I'm denoting it, and states in that Fock space will all have the same memory delta that you started with in this choice. So the standard Fock space is delta equals 0, but you can create other Hilbert spaces which have non-zero memory. And just like the original Fock space did not have any states with memory, two of these memory Hilbert spaces, say labeled by delta and delta prime, are unitarily equivalent if and only if the memories are actually equal. And I should point out that this is not some equality of numbers. It's really equality of functions on a sphere. So the whole function has to be the same everywhere on the sphere. And now what we have done is we have unitarily inequivalent Hilbert spaces labeled by an entire function on the sphere. So we really have uncountably many inequivalent Hilbert spaces. So previously we started with just one Hilbert space, but we didn't have memory. And now we have uncountably many inequivalent Hilbert spaces. So there are lots and lots of these things floating around. And in a certain sense, we really have too many of these because we can't put them together to make a separable Hilbert space in the naive way, just by direct summing over them. But we have these Hilbert spaces. So what can we do with that? So let me just look at sort of simple examples before I go to the actual construction. So in the simplest example where you do electromagnetism with no sources, I mean, this is completely trivial case. There's no actual non-trivial scattering. And so what happens is the memory that you get out is equal to the memory that you sent in with a theta goes to minus theta, which is the antipodal map on a sphere. So you take a point on a sphere and map it to a diametrically opposite point. So in this sense, the memory is conserved. So if you didn't send in any memory, you won't get out any out memory, but that's because the scattering is completely trivial. If instead you had electromagnetism with a classical source, so your source fields are not quantized, then again, if you know what in memory you sent, there's a classical current term, and you can find what the out memory should be. So in this case, in these two cases, these memory Fock spaces are sufficient because once you know which in state you're starting with and what kind of memory it has, you can just use the classical current, or in this case, 0, to just figure out which out Fock space you're supposed to go to. And you end up in that Fock space, and you can write an S matrix for it. But instead, if you send in a massive quantum field, so that is really the case I was talking about. So the source for your electromagnetic field also is quantized. Then if you start with some in memory, say 0, so you don't send in any photons, you don't know what the scattering will give you in the out state for the memory, because for example, we can see it heuristically from this equation. Instead of a classical current term, you get a quantum current term, which has its own fluctuations and all that stuff. So even if this was fixed to be 0, the out memory will have quantum fluctuations in it. Basically, the out state won't be supported in any one memory Fock space. It'll be completely spread out between all these Fock spaces. And I'll show you where all these equations come from in, I think, the next slide or something. So what are we supposed to do? So the standard textbook S matrix, one just pretends that all the states are in the standard Fock space with 0 memory. But because the scattering is generating memory, what really is happening is you're trying to, there's a state that's not in the Fock space, and you're trying to shove it into the Fock space by force. And that's why the S matrix actually has this infrared divergence, which is in the Weinberg-Soft theorem. And it's precisely because of the pole in the 1 over omega, the 1 over frequency thing that I showed you that happens when you have non-zero memory. But this tiny exercise also gives us some idea of what to do. If we had some conserved quantity, for example, something like this case, but it won't be the memory because memory is not always conserved. But if we had some conserved quantity and we build Hilbert spaces on top of conserved quantities instead of the memory, then because the quantity is conserved, you're guaranteed to scatter to the similar Hilbert space. And I'll talk about that next, but I'll pause for a bit here if there are any questions about this part.
Yeah, are you making some gauge choice, which is why you write E is equal to dUA, but you don't have the other part of the electric field? You're writing E in a way that's not gauge invariant. Is that because you're making a gauge choice?
No, E is gauge invariant. It's a component of FAB. So E
I
is
understand, but
invariant.
why have you only written the first term dUAA instead of dUAA minus dAAU?
Because of the asymptotics, the AU falls off faster.
But isn't that, isn't that must be gauge dependent, right? I can choose a gauge where
Sure, I mean, you can choose a gauge where there is no fall off at all.
Right, so that's why I'm asking, you're making some gauge choice when you write this expression for the radiated field?
No, I'm saying this is the simpler expression in the gauge that is the radiative gauge where the electromagnetic potential is smooth at null infinity.
Good, okay, so you're choosing, okay, that's where you're choosing the radiative gauge where it's smooth infinity. Okay, thank you.
Yeah, where it's smooth. I mean, you can make it horribly blow up, right? By a gauge choice, and that'll just be bad.
Okay, thank you.
Okay, so what are these conserved quantities I'm talking about? And these are really the conserved charges at spatial infinity. And there's a whole story about asymptotic symmetries and so on and so forth, but that's a whole another hour talk. So I'm going to just briefly summarize what's going on. So what really is happening is the following. There's a charge at spatial infinity, which is a function of angles. So that's a charge that lives around here. For example, the L equals 0 harmonic component of this is just a standard total charge, the Coulombic charge. And that one can actually write as the charge of all these incoming fields at time like infinity, along with the derivative or divergence of this memory that we can send in from scry minus of the electromagnetic radiation. And this curly D is a derivative on the sphere. And it was conjectured by Strominger and actually can be shown in many, many cases, even in full nonlinear gravity, where there's an analog of these charges, that the out charge and the in charge are related exactly by this antipodal map on the sphere. So no matter what you send in from scry minus, it does some funny thing and then it scatters out. The charge at the in charge and the out charge at spatial infinity, computed at spatial infinity, will always satisfy this. So if we can find a Hilbert space which has some definite charge, that because of this conservation law, it is guaranteed to scatter into itself. So the in and out Hilbert spaces will basically be the same Hilbert space up to this antipodal map. And then between those Hilbert spaces, one can write down S matrix, which is completely infrared finite. And the way this is done was done a long time ago by Faddeev and Kulish. So I'll briefly explain what their procedure basically is. For massive fields, we'll start with these improper states of definite momentum. So these are improper because they're basis, but they're not in your L2 Hilbert space. So we'll start with the momenta of the particles and the momenta of some antiparticles you're sending in, and there are n of those. I've set the number of particles and antiparticles to be equal for simplicity. I'll explain why. And for those, you can compute the charge at time like infinity sort of quite easily it's for every momentum, you start with the constant Coulombic charge of a particle at rest, and then you boost it around. And because you're boosting it around, you'll get some angle dependence, but it'll also depend on the moment of the incoming particles and antiparticles. Now, we don't really want this thing. That's not the conserved quantity. The conserved quantity is the charge at spatial infinity, which is the sum of this and the memory. So at least in this slide, for simplicity, I'm going to construct the Hilbert space where the charge at spatial infinity is 0. And that's exactly why I sent in equal number of particles and antiparticles. Otherwise, you'll never get the total charge to 0. So along with this kind of improper state with this charge, I will pair up some electromagnetic state, which actually has some memory. And that memory is chosen so that this whole sum, which is the charge at spatial infinity, is 0. So what you're really doing is you're sending in all these particles and antiparticles, but you're very selectively sending in the correct amount of electromagnetic radiation so that the charge at spatial infinity is 0. And this is usually called a dressed state. So all your massive particles are being dressed by some photons that you're sending in, which are highly correlated with them. And so, this is how the full dress state looks like. So you start with some photon thing with the correctly chosen memory, your improper particle and antiparticle bases. And as we know, to get an actual state, you really have to integrate over the momenta with some nice function. And that's what I've done. So this is a total dressed state, and it has 0 charge at spatial infinity. And there are actually many states of this kind because, for example, the vacuum obviously is a state of this kind, which has completely 0 charge, where you don't send in any particles, antiparticles, and you just send in the standard vacuum for electromagnetism. And if you direct sum over these particle-antiparticle numbers, you'll get a separable Hilbert space, which is a Faddeev-Coolidge Hilbert space. This whole Hilbert space has 0 charge at spatial infinity. And as I was saying, because charge is conserved in scattering, this Hilbert space will scatter to itself. And so its S matrix, so it will be a map from the Faddeev-Coolidge Hilbert space to itself, will be completely well defined and without any infrared divergences. So that's the Faddeev-Coolidge construction.
Sorry, can I ask a question at this point?
Yes, please, go ahead.
So when you say that you dress these states, so is there a unique or at least a standard way of dressing, or do you introduce new parameters, arbitrary parameters in this dressing?
No, there's no arbitrary parameter. The dressing is basically defined by, so given some particle and antiparticle, you can find the charge at time like infinity just by the standard boosting of the Coulombic charge formula. And the dressing is basically determined by, computing this memory so that the answer is 0. That's unique. So,
right, but if I put one more photon with finite frequency, it will not change this memory. Right?
Oh, no, that's absolutely allowed. So that's why I said, all you have to do is fix this memory, but within that memory, you can pick any state. So you're allowed to add photons which don't change the memory.
So then it's quite arbitrary in that sense.
Yeah. So given some particle and antiparticle, the photon content is not fixed. What's fixed is this. But you're allowed to send in hard photons in quotes along with that state.
What I'm trying to ask is,
yeah,
does this slide really translate into formulas for this finite S matrix at the end? Can we actually compute this order by order, and what does it depend on? Does the S matrix only depend on Mandelstam invariance of the actual particles, charged particles we send in, or do we introduce new parameters by doing this procedure?
Okay, I see. So I would say it will depend on the Mandelstam variables And that's it, because the only extra variable I've introduced, I mean, the Mandelstam variables also show up in standard scattering when you introduce some photon without any memory. So that procedure is the same. The only thing I've done is added this extra memory condition, but this memory is uniquely determined by your massive particles and antiparticles. So there's no extra variable that's been introduced. You just have particles, antiparticles, and you have a bunch of photons. And the only extra thing was the memory, but the memory is uniquely fixed by how many particles and antiparticles you're sending in.
Has anyone actually computed an S matrix in this formalism, say, to one loop order?
No, I don't think so.
Okay. Thank you.
Yeah. Are there any other questions? Okay. I mean, so this guarantees that you have an S matrix, but there's a bunch of other problems with this. Firstly, like I said, I fixed the total charge to be 0. So it's a weird constraint, because you're basically saying, you know, if your experimentalist friend comes and says, I want to scatter 2 electrons, to do that calculation, you really have to secretly hide some positrons. You know, it's usually called particles behind the moon. So you have to hide these positrons behind the moon or in your back pocket and not tell your experimentalist friend that you did this. And that really is because the memory is only supported in the electromagnetic case on harmonics which are greater than 1. So you can't get rid of the total charge by this dressing procedure. You can define a similar kind of Faddeev-Coolidge Hilbert space for any value of the charge. I just did 0 for simplicity. But that value of the charge will not be Lorentz invariant, because if you boost it, its angular dependence completely changes. So if you do a Lorentz boost or even a rotation, you'll take your Hilbert space, which was based on one value of the charge, to completely unitarily inequivalent Hilbert space, which has some other value of the charge. And what this really means is you cannot define any notion of angular momentum or spin for these states unless you had set the charge to 0, which is why I secretly set the charge to 0. And this is usually framed as, you know, Lorentz is spontaneously broken or something. And the last point really is that the massive fields always come with this radiative photon cloud that you have to send in. And if you choose to, you can hide all these clouds at very, very low frequencies. So very low energies for the photon cloud or something. But another issue for like practical purposes is that this photon cloud completely decoheres your state from each other. Because you're really, for different incoming particle and antiparticle pairs, you're sending in completely orthogonal photon clouds with different memories. And so you'll never get some interference experiment in this. You'll never get any interference between these two states that you're sending in from this particular Hilbert space. And this is recent work with Bob Wald by Gautam. And that'll appear apparently, hopefully this week or next. But so I'm just pointing out the issues with the Faddeev-Coolidge Hilbert space that sort of are just, I think, physically relevant. But this is ongoing work with Gautam again. So and we should really write up all of this, but at least in massive QED, all these issues can actually be addressed. So even if the original Faddeev-Coolidge construction has all these problems, you can actually patch up the construction in a nice way so that you get a well-defined Hilbert spaces which don't have all these problems.
Sorry, can I ask you a question?
Yeah, go ahead.
So on the previous slides, when you chose the charge to be 0, as you explained, we can compute this scattering amplitude as a function of Mandelstam invariance. Let me consider, say, 2-to-2 scattering. So it's electron-positron going to electron-positron. So it's
you also have to send in the photon clouds, but sure.
Of course, yes. No hard photons, just electron-positron in the in state and whatever we get in out state. So
no, that's what I'm saying. If you send in, are the electron and positron aligned or at rest? Because if they're boosted relative to each other, the charge at spatial infinity will be non-zero unless you send in some photons to help.
Well, I follow your instruction and I add the memory term and I send some photons and
Okay.
And then, if I understood correctly, the answer to the question by Joao, you say that if I compute this amplitude in practice, I will get that it's a function of just S and T, Mandelstam invariance.
Yeah.
Now, in the usual world of S matrix, we're used to the fact that these amplitudes have crossing. And if I take S in the upper half plane and I go to negative axis, it will describe scattering of 2 electrons, say, or 2 positrons, which have non-zero charge. Now, okay. Total charge. However, now you seem to be, on the last slide, you've been saying that this is a totally different world where Lorentz is spontaneously broken. And I'm a bit confused. So is the statement then that in this formalism, there is no crossing symmetry, or what happens to crossing symmetry? Which takes antiparticles from the out state to particles into the in state. And normally it's an operation which we can do on amplitudes.
Sure, but I mean, the normal amplitudes are undefined. So I'm confused about the question. That the normal amplitudes are completely
undefined.
But
okay, I'm trying to understand how radically. I thought that if we have this function of S and T, and if there is some notion of weak coupling, I start with tree level and I get the same amplitude, it's infrared finite. And then I start computing corrections. Okay, it gets modified and the tree level amplitude is crossing symmetric. It's now, what is the statement if I computed it one loop? What happens to crossing symmetry? I use your dressing, but I still work perturbatively in the coupling. Is perturbation theory breaks down and we cannot compute it, or what happens?
I mean, in the end, I'm going to make the point that you're not supposed to use this Hilbert space in the first place. I'm just showing you a construction that does give you a well-defined S matrix. And I mean, again, you can compute these amplitudes if one wants and ask whether crossing symmetry is well-defined or not. I mean, that's not something I have done.
Okay.
I'm not going to claim whether that's true or not.
Okay, thanks.
Yeah. Okay, so that's the situation in massive QED, but this construction will now fail in every other case I'll talk about. So, for example, it will already fail in massless QED.
Sorry, but I mean,
go ahead.
Can we solve it in massive QED first before we move on to another theory? You said we can solve it, but
solve. Which
you
problem?
said
I mean,
the last sentence you have here is all these issues can be fixed in massive QED.
Yeah, they can be, but you won't get you should wait for my next paper. Yeah, I mean, I'm just being cheeky, but essentially what you can do is you can start with any value of the charge. And if you like, the reason I was saying, this is a problem is because if you boost around all the charges, you get different values. But there's actually a very nice way of integrating over all of those to get very nice Hilbert spaces. The point is you won't get unique Hilbert spaces still. So you can't say I have a unique Hilbert space, but depending on the values of the charge, you'll get a bunch of Hilbert spaces. And then you can use any value of the charge and you'll have, nice angular momentum and spin of the states. And that actually also solves magically the third problem that you always have to send in a photon cloud and it'll completely decohere and all that. So that's the summary of what happens. But I mean, I didn't spend a lot of time explaining this because it'll only work in this case anyway. And when you go to other cases, I mean, it'll all fail again.
Okay, thank you.
I think there is also, I guess, here in Bootstrap, there is a sense that even going from this formal construction, massive QED, to actually to be able to do some computation and to make some non-trivial statements would be great. So
no, absolutely, I agree. I mean, here I'm just saying, okay, the S matrix is guaranteed to exist. I'm not giving any calculational procedure. I mean, I absolutely agree with that. It'll be nice to actually have some way of computing the S matrix. Yes.
And easier, say in the Bootstrap, when we can get some where we know how to do things, it's based on unitarity, analyticity, and crossing. Do you have any sense of which of these, say, three things will be present if we do that in here? What happens to analyticity? What happens to unitarity and crossing?
Okay, so this is sort of a guess. So I mean, don't
Okay.
hold me to this or something. I think unitarity will be fine, given that the S matrix is completely well defined from a in and out Hilbert space. So I would expect in massive QED unitarity to be okay. Analyticity would be in the Mandelstam variables, correct?
Yes, exactly, yes.
I would suspect that also holds, but I mean, yeah, that I'm sort of putting a caveat on. I mean, because it really depends on how these S matrices depend on the Mandelstam variables and all that stuff. But my guess would be that analyticity would hold in the same way as we do for standard S matrices. Crossing, I'm not sure of. That's the only one I'm not sure of because, because of this issue that you're always in the zero charge regime of the whole game. But again, these are my guesses for what happens, and it'll be nice. It'll be very nice to know whether that all works or not.
I have one question here.
Mm-hmm.
So first of all, you are considering this Hilbert space where you are telling that you will add this memory term and those will be now your scattering states, right?
Yes.
Now, do I think that this dressing of the photons will be for all energy photons, or these coherent states have some integral over the photon phase space? So is there any cutoff there?
No, this is without any cutoff of anything. And
so that means hard photons are also included in the dressing if the photon momentum really going to infinity, 0 to infinity in the phase space integral of the photon?
Yeah, all you have to make sure is that the memory term, the zero frequency part, is the correct one, so that you set the charge to 0. But after that, you're allowed to send in any state.
So that means in terms of this S matrix, if I compute suppose 2 electron or 2 electron positron going to electron positron, we won't ever able to see that some radiation is coming out.
Why not?
Photon radiation is coming out. So in a sense, should we think that if this is the true S matrix, we never can see in LHC some photon or some other things?
No, I disagree. Why do you say that we can't see any electron or photons coming out?
No, electrons we can see. If you are really integrating out really the all photons, all moment of photons, and that is included in the dressing.
No, it's not integrated out.
Yeah, it's like in the
it's
dressing.
Included.
Yeah, it's included.
Yeah, so you can find how much photons come out. I mean, just if you just stare at this state, for example, let me just go here. There is photon. So if you have, LED detector to look at it, I mean, if you have a camera, it'll see these photons.
Okay.
There are photons in your state. So I don't understand why one would claim that the photon is not observable.
Okay, so we can split the Hilbert space and individually observe the electron and photon separately also. Okay.
Yeah.
Great. And another thing, just about the unitarity you were speaking about, so suppose if I think this optical theorem and we want to insert this resolution of identity, right? In the intermediate states, should I include write down the sum over states as the trace states in the intermediate states, or only the particle states, not the photon or other thing, just to understand?
I mean, this is a separable Hilbert space, so there is a basis, and you can use the resolution of the identity for that Hilbert space. You can't use the standard Hilbert space basis for the resolution of the identity.
Okay, thank you.
So can I quickly ask also follow up?
Yes.
As you said, this Faddeev-Kulish is a very old construction. So
Correct.
I think people have been doing some computations, but you said they haven't computed this amplitude. So what has been computed using this?
Yeah, that's a good question. I mean, I would say that people got distracted by all these things on the third slide.
Okay.
You know, like if people started, I mean, again, this is, I mean, I'm not claiming to be historically accurate or be in the minds of these people or something. But I think the IR finiteness has been checked. Yeah, I think a lot of people got distracted by, oh no, Lorentz is spontaneously broken. Now, how do we fix it or something? But I think there's some work by Matt Schwartz and people who have computed some amplitude, as far as I know. But I'm not sure at what, you know, how many loop levels or something that has been done.
Okay, thanks.
Sorry, we are slowing you down very much, but since we are
that's okay.
general questions, is there a simple summary of how your approach will differ from the one by Matthew Schwartz and Hannes Dottir? They also claim to define some finite as matrix.
Yeah, I think, so if I remember that work correctly, actually Gautam knows more about that, but I'll just say a few words, and I think if Gautam wants to chip in, and if I said something really wrong, he should correct me. I think they're trying to write the S matrix between the standard Fock space, but they're changing what the S matrix actually looks like. So they're, you know, I think it's phrased as we're dressing the S matrix and not the states or something. I think, and that sounds problematic to me, because the S matrix is basically telling you what the time evolution of your theory is, basically, between infinite times, but it's really telling you what the time evolution of your theory is. So I don't think you should change how the S matrix works or something in order to get rid of this IR divergences. Gautam, did I summarize that correctly, or did I say something stupid?
Yeah, that's effectively correct. I mean, so basically they define what's called a hard S matrix, which is just a map between this in and out, you know, standard Fock space. And the idea there is that, you know, in order to define that, they try to develop some prescription for such that the S matrix is, you know, they attempt to, you know, define such an S matrix that cancels out IR divergences within the definition itself. That's not really, I mean, you can't really talk about any of the infrared structure of the outstate itself. Like the outstate is undefined in their construction. It's only the, you know, the state up to an IR cutoff that is put in basically by hand.
You're saying they're implicitly using some sort of factorization between the hard part and the soft part. The hard is a root summary.
Yeah, effectively. I mean, like
Yeah.
they're trying to find a prescription such that they can like systematically compute inclusive cross sections, but that's not. I mean, so the question that we were asking, or Karthik is talking about, is just, does there exist a genuine S matrix between in and out states that include all observables? And so they're basically orthogonal questions. So I guess it depends on what you're interested in specifically as to whether or not you want to use that approach.
Oh yeah, I should have mentioned the inclusive cross-section story is not affected by any of what I'm saying. Yeah, we're genuinely asking, does the S matrix actually exist as an object?
Can I maybe add one thing to this?
Oh yes, hi.
Hi. Yeah, I just wanted to say that the reason why we use Fock states is because we are basically looking at this in the Heisenberg picture. So our states would still be dressed at time equals minus infinity and time equals plus infinity, because that's taken into account in the evolution of what we call the S operator. So I'm guessing it's not so different from here, but I mean, the important part for us was to not take any cutoffs on the 0.3, I guess, here. So it would be interesting to work out the differences, if there are any.
If I could ask a question then, I know this isn't your talk, but the states in the Heisenberg picture can't act on the standard, if states with memory in the Heisenberg picture can't act on the standard Fock space. So there has to be a different redefinition of the S matrix. Maybe we can just talk later.
Yeah, absolutely. Absolutely. Let's do that.
Okay. Good discussions. Okay, so what happens in massless QED? So now instead of sending in a massive scalar field, I'm going to send in a massless scalar field. And the only kind of thing that actually changes is instead of some charge at time like infinity, because your charged scalar field will also come in from null infinity now, you get a current term. So I'm just calling that J. And that will depend again on the momenta of particles and in antiparticles. And to do the same kind of Faddeev-Coolidge construction, you have to put charge equals, and again, I'm just doing charge equals 0 for simplicity. You again play the same game where you find a memory such that this whole thing is canceled to give you 0 charge. But the funny thing is that suppose you sent in a particle, and the story is the same if you sent in particle, antiparticle pairs, and so on. This current term actually includes a delta function in angles. So p hat is kind of the angle at which the null particle is coming in. And if you find, again, there's a unique solution, but if you find what that solution is, it actually diverges when the angle coincides with the direction that the momentum is coming in. And this really is related to this collinear divergences that happen in massless QED. And again, like having a divergence usually isn't a problem unless some physical quantity diverges. And here actually it does. This kind of memory actually isn't square integrable on the sphere. It's too singular to be square integrable. And I haven't given you the proof here, but basically the photons that you need to dress your particles with to sit in this Hilbert space have an infinite energy. So you can still dress your particles and antiparticles with these photons with memory, but all those states have infinite energy. I mean, of course, except the vacuum where nothing happens. And as far as I'm concerned, I think that's a bad idea for this dressing. And this is not special to the 0 case. This kind of collinear divergence will happen no matter what charge you picked here. The singular part will always be divergent in this sense. And again, I should point out, you can, if you, we of course don't like diverging energies, but you can smear in the angles a little bit so that the memory does become L2, and this has, finite energy, but then you're not in the Hilbert space, which has a definite charge. Your charge will also have some smearing in it. So the strict Faddeev-Coolidge construction actually does not work in massless QED to give you physical states. Okay, next theory, which is linearized gravity with massless sources. So for the linearized gravity case, again on Minkowski background or something, there's a very similar story where the E is replaced by the News tensor, which has 2 indices. And there's the gravitational memory delta, which again has 2 indices. It's symmetric and traceless on the sphere, which is the integral of this News. And a very similar story holds that your outstate generically will have memory, even if your in-state didn't, and therefore you have to do something about these memory states. And the quantization actually proceeds very similarly to the electromagnetic case at null infinity. And you get states which are in the standard Fock space, which have no memory, and you get a bunch of memory states floating around. And again, memory is not conserved in this gravitational scattering unless you're in strict linearized gravity with no sources. So if you try to repeat the Faddeev-Coolidge construction, what you now get is the charge at spatial infinity really is sourced by some massless stress energy tensor. And instead of one derivative of memory, you get just two derivatives of the memory. And if to solve again this equation, again, the 0 is for simplicity, and you can find a unique solution provided that you actually had only set the L greater than equal to 2 harmonics to 0. And the reason is that the L equals 0, 1 harmonics actually are the 4 momentum objects, but computed at spatial infinity. It's the 4 momentum of the state you're sending in. And that you can't set to 0 unless you're already in the vacuum in Minkowski spacetime. So basically, you don't have positive and negative mass particles. So if you send in some mass, you can't hide a negative mass particle behind the moon to actually fix that like we did in QED. But there is some things are sort of similar, and actually it's much nicer in the linearized gravity case, which is the stress tensor again has this delta function in angles. But because we had 2 derivatives, the memory is actually only log divergent, which is still a collinear divergence, but it is square integrable. So the graviton dressing that you're putting on actually does have finite energy, and it all seems nice. But then you again run into the trouble that this condition that the higher harmonics are 0 is not Lorentz invariant. So you can start with something which has all L greater than equal to 2 harmonics being 0, but if you Lorentz boost it around, you'll already pick those up. So even though the energy is finite for these dressed states and so on, again, you'll not have angular momentum and spin for these kinds of states. Okay, but now full nonlinear GR completely destroys this whole process. And again, I'm going to be agnostic about, I am using general relativity, but the quantization in the bulk spacetime, I'm going to be very agnostic about. And the phase space at null infinity is actually a linear phase space, which looks exactly like linearized gravity. The only difference that shows up, and I'm not putting in any matter fields, it's vacuum GR, just again, for simplicity, we can put in matter terms here. The charge at spatial infinity, which is now, the charges associated to the BMS group and so on, has this 2 derivative of memory term, but it has this Bondi nu squared, which is a mass loss kind of formula. So it's because even though we are at infinity, sort of gravity interacts with itself and it gives you this nonlinear term. And all these memory Hilbert spaces still exist. And again, memory is not conserved, which is the same as in the previous cases. But now you run into really big trouble with trying to find addressing. So if you say you want to set this term to 0 or the higher harmonics to 0, you can start with some state and then choose a memory so that you make this charge 0. But picking some memory value does pick some news, but that news then again contributes again into this term as a quadratic object. And then you again have to correct it with memory, but then again that contributes into this. And actually we prove this very general theorem that if you want any state which has a fixed value of the charge, then that state has to be vacuum and its charge has to be 0. So the Faddeev-Coolidge procedure will just give you 0 charge and the vacuum in gravity. And there's no other actual state in the Faddeev-Coolidge Hilbert spaces. So nonlinear GR just completely destroys this entire program of constructing Hilbert spaces. Are there any questions about this one? I only have 2 slides left, so hopefully I won't go really over time. Okay. So now I'm going to make the point that all these issues, all these problems in every case are mostly because we're trying to ask for a Hilbert space. There's a completely well-defined operator algebra in each case. And there is a huge supply of states. For example, all the states in these memory Fock spaces are completely fine. They have finite energy and all that stuff. You have to fix the angular momentum correctly, even in that case. But the issue really is that you cannot force all the in and out states into one big Hilbert space. And that's the issue that that really is what's causing the trouble in all these constructions. Okay, so what do we do? And I would say, you know, that the quantum theory really gives you all these operators and algebras, and you can ask for Hilbert spaces, but trying to squeeze in all states into a Hilbert space really is problematic. So, for example, there's no issue really with anything if you just define in and out states as a bunch of correlation functions. So omega is my state, and you just, if you give me a list of correlation functions of all the operators in your theory, that basically defines for you a state. And if you give me any such state, it lives in some Hilbert spaces, but it's not that all states can be put into a single Hilbert space. That's really what was going wrong with all this Fourier-Coolidge business in the cases it failed.
So here by operators, you mean local operators? Are they like localized or at least with some?
These are local operators on null infinity in the way, I mean, you know, for example, the electric field in the electromagnetic case and the News operator in the gravitational case. I'm not going into the bulk. These are all asymptotic operators and asymptotic states at null infinity or time-like infinity.
Okay, thank you.
And essentially, any notion of scattering or time evolution essentially is given by some, to distinguish it from some S matrix, I'm going to call it dollar or something. This is a notation borrowed from Hawking's paper, which is sort of a map between in correlation functions and out correlation functions. And this kind of seems pretty simplistic, but we can ask for other things from this, like the conservation of probability is very easy to formulate. The fact that there's no information loss can also be easily formulated by saying, you know, pure in state should go to pure out states, for example. That will have no information loss. And the issue really is, and I think a lot of people and questions here were basically asking, you know, how do you actually practically compute this? And really my answer would be, I don't know, because the usual methods like Feynman diagrams and LSC reduction do not work because they're really assuming a single Hilbert space for the S matrix to work out. And there's a paper by Hawking from 1976, which I think has very interesting ideas, but he was trying to do information loss kind of things, but he still assumed that there's a single Hilbert space. So mostly you can define scattering purely algebraically on correlation functions, but how to actually practically compute it, I think we need to all think about more. Thanks.
Thanks a lot, Karthik, for a very nice talk. So let's.
Oh, I can bring up the slides again if someone wants to point at things. So just.
Yeah, and yeah, let's open the floor for more questions.
Yeah.
Yeah, so yeah, Joao, please.
So let me ask, maybe Biswajit asked you a similar question, but let me ask again to see if I really understand.
Yeah.
So let's take the simplest case of massive QED, and let's do like also like Sasha says, just scatter electron positron, so total charge is 0. And now I just want to understand even physically. So we send these guys in, and they will come out as again electron positron. Okay. possibly other pairs can be produced, but let's not think about that for now.
Mhm.
But let's try to measure photons very precisely. I would think that if we really make a very big detector that can detect very low energy photons,
Mhm.
we would measure very low energy photons. And if we make a bigger detector, we would measure even bigger. So there will always be, if we have a big enough detector, there is zero probability that we don't measure a photon. So
Correct.
if this is true, then, I mean, in what sense are we ever going to define an S matrix? Because we can talk about dressing as much as we want, but in the end, if we really try to measure these things, if we don't put a cutoff in how low frequency we can actually measure, any scattering to a finite number of photons is zero. Probability is zero.
Yes. No, I mean, I'm not claiming that we should build a gigantic detector to surround the universe. I mean, for practical purposes, you'll always have a cutoff. That's fine.
But this is what I asked you. You told me that Faddeev-Coolidge doesn't have a cutoff, and is defining
Faddeev-Coolidge does not have a cutoff. Yes.
So how can you not have a cutoff and you get finite S matrix elements? It looks to me impossible because physically we know the probability is zero. If you don't have a cutoff, you can always measure an extra photon. I don't understand. What's the physical meaning of the finite amplitudes that Faddeev-Coolidge define or someone defines for massive QED?
Wait, I'm confused. Are you saying that if you don't build a detector that's as big as the universe, then you'll never detect photons? I mean, that's false because I have a camera on my computer.
No,
so
I'm
confused about the question.
What I'm saying is that if I have a very big detector, I can always measure a photon.
But you can measure photons with small detectors also.
Sure, that's okay, but that goes in the direction that I'm complaining, that the probability, suppose I want to compute the probability of positron plus electron going to only positron plus electron, very exclusive amplitude.
Okay.
So this
that amplitude might be zero, and that's
should be zero, right? Should be zero. Unless
I'm saying it might be, so but it's okay. I mean, if a particular amplitude vanishes, that doesn't tell you anything.
Right, but Faddeev-Coolidge computes an amplitude that's supposed to be
the objection is that you need some resolution for how many soft photons you're going to include. So it's passing that there's no cutoff. What is the prescription implicit in Faddeev-Coolidge?
Thank you, Leonard.
There is no prescription for a cutoff in Faddeev-Coolidge. I mean, you can compute all amplitudes that Faddeev-Coolidge tell you.
But the objection is that all exclusive amplitudes are just zero, and so if something is non-zero, has to be at some level inclusive, and that's what we are confused about. If it's inclusive, then it comes to the including.
Yeah, I mean, I never claimed that the inclusive amplitudes are not non-zero. The inclusive amplitudes, I mean, you can still put a cutoff and then compute the inclusive cross sections. That's completely okay.
That's the standard thing that people do.
Yeah. No, I'm not claiming anything is wrong with inclusive amplitudes or computing inclusive cross sections.
The confusion is if there is a finite thing that is claimed to be computed and it doesn't have a cutoff, what is it?
I mean, one can ask the same thing about, why memory? Because you cannot measure for infinite time. I mean, again, I'm not claiming this as a practical problem. There's no actual practical problem with just computing inclusive cross sections. I'm saying if one really wants to take an S matrix seriously, there are all these issues. You can say we don't want to take the S matrix seriously, and that's completely okay. I'm fine.
No, Karthik, but we're trying to do the opposite. We want to take the S matrix seriously, so we need exclusive amplitudes. Right? In the S matrix, everything is exclusive. But just physical arguments make exclusive amplitudes all zero. So if someone comes and proposes some way of defining finite, non-zero, exclusive amplitudes, they need to explain us what do they mean physically.
But if somebody gives you the exclusive amplitude and you can tell them how big your detector is and you can go and compute it. I mean, once you have the exclusive amplitudes, you can then impose your detector size cutoff and calculate probabilities. Are you saying those are all zero?
No, but
Maybe I could also jump in and add to Karthik's comment, or maybe a clarifying comment. Is that okay?
Sure, thanks.
Yeah. So the Faddeev-Coolidge amplitude is the amplitude for producing your favorite electrons that you're interested in, plus, these soft photons. And these soft photons will have a particular distribution, but will be supported at very, very, very low frequencies. And so your cross section will have support at very, very low frequencies. And when you want to ask, what does your detector see? Well, you need to know how big is your detector, how long is it running for, and then you truncate the Faddeev-Coolidge cross-section at those scales, and that's what you measure. Is that clear?
But in the Faddeev-Coolidge procedure, in the dressing, aren't you integrating over all energies? It's not only soft photons in this dressing, right?
So I think that's another confusion. So the dressing is just telling you what kinds of electromagnetic states are required. You're always like, now when you're asking what outstates you get, like if you're saying 2-to-2 electron scattering and you're saying that you for some reason are not going to get any hard photons, Faddeev and Coolidge will always say you are guaranteed to get some very, very low frequency photons. But that's not this, like in the formulas that Karthik was writing down, he was just allowing you to tensor in any electromagnetic state, hard and soft, but the soft stuff just is prescribed for you now. Is that clear?
Photons are not integrated over.
Is the answer to Joao's question then that if I do this Faddeev-Coolidge business and I have my detector of size L, I will get something finite and it will be partially inclusive, but the non-trivial part is that I take a limit of an infinite detector and A, this limit exists, and B, it is non-zero, the result. In the limit of infinite detector.
Yes, that's correct.
Okay. Yeah.
But you're saying that nobody has ever computed this concretely, even in one loop. There's no actual expression.
Maybe I can point to a paper by Lavelle and McMullen, which take the Faddeev and Coolidge construction and compute it basically with energy cutoffs. So that way you don't generate UV divergences, but your infrared divergence becomes basically a log of the cutoff. So I can post that paper in the chat and you can take a look at what those amplitudes look like.
Hope here can I make a point here? I agree that with cutoff you can make the S matrix IR finite. It's okay, but can one really extract the IR finite piece after removing the IR divergence piece uniquely? Or it really depends on how you choose your cutoff, like L, if you have if it is logarithmic divergence, then I can think setting L cutoff or setting 2L cutoff will affect my finite piece after subtracting out or removing the divergent piece.
Yeah, absolutely.
So
how you cut things off in the UV, or how you put a function into, basically the Faddeev-Coolidge construction says that you have to have some function that limits to 1 in the soft limit, right? So that you cancel the soft divergences. But outside of that, I mean, one has a choice.
Right. For UV, I know this renormalization is there. So, okay. But for IR, how I can make sense of two different IR finite pieces? Like in one regularization parameter, I have some finite piece. In another, I have another finite piece. So which I should take seriously?
those just correspond to different memories. You're just looking at different states. Right, so in my slides, I mean, the IR, the coefficient of the IR divergence, if you have some state with memory, its frequency part sort of diverges as 1 over frequency. But the coefficient of that depends on this memory object, and different memories will count as different states.
Right.
Is the point that this non-uniqueness is somehow fixed by you imposing that the total charge is 0 and in this sense restoring Lorentz invariance?
Correct, yes. Okay. In the 0 charge case, yeah, that is correct. Because the memory is determined by setting the charge to 0 so that you get states in that particular Hilbert space. But you can set the charge to something else and then you'll get some other memory floating.
Yeah.
And so yeah, the amount of softness in quotes that you have just corresponds to different Faddeev-Coolidge constructions for different charges. And they're all states, they're all perfectly fine states. You just live in different Hilbert spaces with different charge values.
But somehow you say there is a canonical choice, which is Lorentz invariant.
If you want a fixed definite charge, then the only Lorentz invariant charge is 0.
Yeah.
But if you allow for spread in charges, you can make that spread Lorentz invariant, but then you don't have definite charges.
So if we can be really explicit and just take the formula from Faddeev and Coolidge's paper, what you're proposing is just integrating basically up to infinity in all the momentum space integrals for the photons, and that would be the Lorentz invariant construction.
No, I'm allowing for any photon profile. So yeah, I guess I'm confused about what you mean by integrate over photon momentum.
Oh, just because in their paper they have a formula for the operator, right? A formula for the dressing operator, which acts on the state, and then one has a choice basically about what to integrate over, right? So there is the phase part, and then there is the real emission part with the photon creation annihilation operators, right? Yes. And in all of those integrals, we have momentum space integrals over the momentum of the photon.
Yeah, the actual photon, I mean, those are the hard photons, and those you can have to be anything you want, right?
Okay, but wouldn't that get us different finite parts for the S matrix? If we take different choices of how we integrate over the hard photons?
No, the hard photons are the ones that are not at 0 frequency. They're supported away from 0 frequency. Those are not the ones that are used for the, or at least the one I wrote, those are not the ones that are used in the construction. It's the 0 frequency memory part that is used for the dressing. The hard photons, you can have any of those if you want, but they'll all be in the same Hilbert space. They'll all be different states in the same Hilbert space is what I'm saying.
But as you say sorry.
I think the confusion here is that Faddeev and Coolidge, it seems like, make a big deal about a choice of preferred actual dressing. And what we're clarifying here is that that doesn't matter. Like,
yeah, I agree.
There isn't really a choice of preferred dressing. It's just, you know, the only thing that's preferred is whatever you do, whatever dressing you do, you have to fix it at 0 frequency in a particular, in the way Karthik is described.
Oh, absolutely. I agree with that 100%. I'm just trying to see what the finite S matrix element would look like in practice if I wanted to compute it. So I'm guessing what I don't get is the uniqueness of how it's uniquely fixed, or if the finite parts are uniquely fixed or not. I guess that's my question.
So the finite parts are just what you get, like, from the scattering theory. You send in stuff and then you get out some possibly hard photons, and you could get those. All that's guaranteed is the soft part. So there's nothing unique, because the dynamics is going to tell you whether or not you get a hard photon or not.
So if I didn't measure a hard photon, if I did the scattering and I did E plus E minus to E plus E minus, and I didn't measure any photons, what would I what would I put for my dressing? What would be the finite part?
Well, so it's, yeah, so you're asking a question about dynamics. So like the outstate, you would have to ask, you can ask for the probability amplitude, for example, for an in E plus E minus that is very, very, very softly dressed, and the E plus E, outgoing E plus E minus that is, has a similar dressing or similar, very, very soft dressing.
Yeah.
And you will probably get a non-trivial amplitude for that. And then if you try to calculate the probability amplitude for emitting that same dressing plus a hard, a very hard photon, you might get zero. That's the content of the statement. I mean,
but
so
just
you would have
when you say very, very soft, how do you impose that in the dressing?
Well, yeah, it's whatever choice you want to make for what you mean by soft.
So you put a cutoff, basically.
No, I mean,
no, it's not a cutoff.
There's no cutoff. It's just whatever, you're allowed to choose whatever dressing you want. And as long as it's there, I mean, maybe what you're saying is like the outstate is not defined just by, what, the outstate is defined by, a particular choice of outstate. You need to have chosen a particular dressing. So a specification of an outstate isn't just E plus E minus. You have to have chosen a particular dressing. So you're calculating probability amplitudes between particular choices of dressing and particular choices of dressing, but the full Hilbert space is invariant under that choice. You can choose whatever choice you want, and they're all unitarily equivalent Hilbert spaces.
But
they're just different states in the same Hilbert space, though.
Yeah,
that's the point. But they're different.
But I would
states.
predict different amplitudes then.
Yeah.
So the finite part doesn't have any significance in this construction.
No, it has significance because it determines for you a particular state. But the only point I'm making is that they all live in the same Hilbert space as long as their zero frequency part is the same. The memory is the same. That is the only thing that's determined. Everything else on top of just the zero frequency memory part are different states in the same Faddeev-Coolidge Hilbert space. And you can have different amplitudes for them. Yeah.
Okay, thanks.
Yep.
Just to make another comment, like already I think in Faddeev-Coolidge's paper, they introduced this super selection sector, which basically possibly in your language continuously map between your different Hilbert spaces, and that in the zero frequency limit reduces to the memory, right? If I am correct.
Usually super selection sectors are labeled by conserved charges. So they would correspond more to the charge sectors, not to the memory sector, I think. But again, I should go back and look at what Faddeev-Coolidge exactly used it for. But sometimes it has been used for memory. But yeah, go ahead.
Yeah, now if I just try to see the recent paper of Strominger and like Nima and their collaborators, they fixed that the dressing, in the dressing, there will be only this, say, 1/omega pole, which is, the memory, times there was this function, which was the super selection function. They put it set to be 1 from some, like if I remember, like, this condition came from some like celestial amplitude stuff, but then so that means they are really staying in a particular Hilbert space, not like you have this infinitely equivalent Hilbert spaces. So just try to connect. Can you compare with your thing with them?
Yeah, so I think this extra function that they want, and I mean, I know the papers you're talking about, and they make a big fuss about whether that function should be 1 or whether that function should be start at 1 and then oscillate or something like that.
Right.
And that's what they're doing. And I think, I mean, it's not 1, it's supposed to be a step function or something, right? I think that's the canonical choice they make.
Yeah, right.
And that is irrelevant. So, I mean, actually a step function probably is bad because it has a, it's singular, but you can use any function that starts from 0. It can oscillate, it can do anything in between, and then it ends up at 1. Right? For example, you can choose the step function, or you can choose some, tan hyperbolic thing, or you can choose some function that does some really crazy things, but starts at 0, ends at
1 when you take the frequency of the photon to be 0. Is
Correct.
this the statement? Okay.
because
Karthik,
that
I
value
think
is the memory.
this is really the crucial problem that we have in communication here, because you're saying it doesn't matter to get a finite answer, right? To be in the same Hilbert space or something.
Correct.
But that's not enough. We want to actually compute something. And to compute something,
Yeah. I'm not claiming that
have,
computing this S matrix is easy or anything of that sort. Sure, yeah.
No, but so we have to make sense of, find some prescription that is like to every charged particle associate a particular clause, and then you compute something, and then in that scheme, the S matrix is unitary or whatever, and Lorentz invariant. So this is what we're looking for. If you tell me you can put any function, get a finite answer, but then a different function gives me a different S matrix, and everything is like, it's useless, you see? This is the computation problem that we're having here.
No, I'm not saying a different function gives you a different S matrix. A different function just tells you that you started with a different state. If you start with different states, obviously their amplitudes are different.
Yeah, but what does it mean a different state, in the sense that if you change this function, it always goes to 1, but you change it at finite frequencies because you have to choose something. So
yeah, it means you're adding in hard photons.
What is the right thing to describe the actual scattering of E plus E minus?
Okay, you can tell me what in state you want.
Well, I want E plus E minus.
Without any dressing, then there's no Hilbert space that I know of that works.
But we can do the experiment. Are we physicists or are we mathematicians? I mean, I'm asking you a physical question. How do I describe scattering of E plus E minus? You tell me there's no Hilbert space? That's not an answer for a physicist. What can I do with that?
Sure. I mean, again, like I was saying, if we don't want an S matrix and a Hilbert space, I'm happy to not have an S matrix and a Hilbert space. You can define your states perfectly fine as correlation functions. And then I'm posing the problem, how do we calculate the S matrix? Because standard techniques do not work. And that's exactly the question you're asking. And I think we're agreeing on that. What is a practical computational way to calculate S matrices for these things without going into some Faddeev-Coolidge construction, which, I would say the Faddeev-Coolidge construction is really artificial. So, we're agreeing on that. And I don't have some magical answer for calculating these things. And I agree, I can send in electrons in an experiment and it all works in real life.
Yeah, I guess the point is that we're trying to push you is that we would really like to have a calculation and some explicit thing that we can then work with Bootstrap or some other idea. And
I agree. And I would also like
trying to push you.
I'm doing the 0th step is the calculation with Hilbert spaces and standard methods even well defined? And the point is it's not. Okay, and you're basically asking me, okay, then what do we do? How do we calculate anything? But I agree that's not resolved and I haven't told you anything because I don't know. But the point is I'm just saying that the standard methods that we use does not work for massless fields. So we need to find something, and what that something is, I don't know at the moment.
Sounds good. Thank you.
Yeah. So yeah, if someone has a Bootstrap kind of way of doing this, that'll be really amazing because I also want to know the answer.
Okay, I guess it's a good point to all go back to Compton scattering and Peskin and Schroeder.
Yes.
And to do the one loop properly. So would be really great to have this formula for finite S matrix. Okay, so I suggest we thank Karthik again. This was a very, I think, motivational discussion, and we should really think hard how to make it work. And hopefully someone will have this formula soon.
Yay. Great, thank you for having me.
Okay, thanks everyone. And bye-bye.
Bye everyone.